So this much we actually already knew. There's nothing new that we have covered so far. But from here, the things look slightly more, we'll go in a little bit more detail on how to do these things a little better. So essentially we started by doing, by just calling something Q which has all the vertices because we have not selected any. And we will give each of the vertices to be a label of infinity, which is called, which we're referring to as key here. And pi is the parent of that. So initially I will select one root node, give it a label of 0, add its parent to null. And then while Q is not empty, so that means while there are still some vertices on the right hand side, we will keep doing this thing. We will bring the least labeled vertex over to the left hand side, and we will update the labels of the other vertices that vertex is connected to. Right? Is this articulation clear that it's the same as what we did previously? Okay. So here is the running time of Prim's algorithm. We could say, if we don't use any heap or anything else, then we can say that lines 2 and 3, this takes order v time, right? Because you're just assigning a label to each vertex. And here, now here we already have to be a little careful on how we count it. This loop runs order of n time, right? And this loop runs, well, can potentially run order of n time, right? So this should be order of n squared time here. And then we have some constant time within that. But then we have to be a little bit more careful to say that actually this part only runs together order of m time. So the line 8 and line 6, while we can multiply that, we really shouldn't. So line 6 can run a maximum, will run a maximum of n times, right? Or n minus 1 times. And line 8 can run order of n times maximum during each run. But a different way to see this is that the total number of times that this will run is m times. And this observation is the key for us to go any further really here. So is this aspect clear? So if there are two nested loops, then we always try to say, okay, then just multiply their complexities, right? But what we are saying here is that that's not the right way to see it. The inner loop itself has its own total number of runs that's bounded. So what you're doing here is once you bring a node over from the right-hand side to the left-hand side, then you try to update the labels of all the vertices that it's connected to. You will do that for each edge once. Right? If you do that for each edge once, that means this loop will only run a total of m times. In some, it can go run too many times on one, and then a little lesser times the next time. But together, in all of these iterations of the while loop here, together this for loop will run a total of m time. However, the line 7 itself takes some time too, because if you're saying that extract min, that does not mean that it is a minimum time, that it's a constant time operation. To find, given an array of numbers, to find the smallest number takes order of n time. So that means that these lines together, 6 and 7 together, could take up to order of n squared time, if you do not implement it without any heaps, etc. So if you just implement it as a plain array, then because of lines 6 and 7 here, there's an order n squared element here. And there was order e element here because of this aspect here. So this aspect is clear here. Okay, then let me go a little further and we will say, okay, then of course the performance really depends upon how we choose to implement the queue. So on how we can do that, then the better it will be, right? So if we use that as a heap, then we will have to do, then we will be able to do a little better because the line 7 will not take order n time, right? So the line 7 will take order of log n time. Right? So if let's say you implement it as a binary heap, then the line 7, which is to remove the minimum node from a binary heap, will take log n time. So then we will have an order of n log n time. And therefore I could, by the way, you notice that I'm using E and M interchangeably and V and N interchangeably. That's a common convention in graph theory. N stands for the number of vertices, M stands for the number of edges. So as I said, if we use a priority queue, then I could conclude that my line 7, because it takes order log n time now, not order n time, that this is going to take order of v log v time. So let me go back to that. Order of n log n time here, n times log n time, right? But if I were to claim that now, because if I change that, my time is going to go from order of e plus v squared to e plus v log v, or order n plus n log n, then I will have a mistake in my conclusion here. And I want you to find that for me. What are we missing out? So I said if we don't use a heap, if we use a plain array, then this is the time, right? And so that built up the motivation for doing that a little faster. So we said we could use a queue, we could use a heap, and that will take a log n time here. And if we do that, then if we were to claim that it's now going to take order of m plus n log n time, then that would be a problem. So what are we missing here? So look at this algorithm, and where else are we doing anything that would change based on the data structure? So essentially all I did was I changed the data structure from an array or a list to a heap, right? And we said based on that, this is now going to go down, but is there something else that's going to go up that we have to now take into account?
You're searching for V and Q.
Oh, which line number is that?
9.
No, actually not. It's not a. So, good question. These are all implementation-based questions. So all detailed questions are good at this point. But it could, but I can argue this way that I will keep an array of vertices. I will initialize all of them to 0, which would say that they're on the right-hand side. As I bring them to the left-hand side, I will mark it as 1. So when I want to check is it on left-hand side or right-hand side, I do a constant time array check, right? So this does not take any time, whether in the first version or in the second version. But good question. So what else? So again, let me repeat the question. I said, first of all, we analyzed it. We said if we don't use a heap, then this takes this much time because of this time here, this time here, this time here. And then we said if we change an array to a heap, then this time goes down. Extractment goes down from order n to order log n. But my question is, what else is affected?
Is it the time to build?
Heapify?
Good point. Yes, that's point 2. But then I could say that heapify actually only takes order of n time. To build an initial heap only takes order of n time. So that is essentially no different from then just putting that in a list. There might be a constant hidden there. So building an array is maybe really n time, while a heapifying might be 5